Hello, today we'll discuss about magnetic materials. So to start with magnetic materials, first we're going to take the basic idea about the magnetic materials, then we'll go for the basic theories, and then we'll compare the different types of magnetic materials. And at the end we'll discuss about the applications of the magnetic. So magnets was available from the beginning of human civilization, but the use of magnetic material was the most important one in the modern days. As the application increases, so magnetic material, the start of magnetic material was important. So the first, let me just talk about what is magnetic material. So long back, 200-300 years back, people start thinking magnetic materials as a part of number of small magnets. So when you think about a magnet, so the first thing comes in our mind that you have a bar magnet type of thing, and one side there will be N, and the other side this will be S. So this is the beginning of discussing about the magnetic material. So if you think about the magnetic material, so the simplest way to think this magnetic material that it consists of some number of bar magnets, so small bar magnets. So now in school days, if people start thinking about bar magnets, so it helps that if you have some external magnetic field, you are taking some external magnetic field, one side N, another side X. So all the S will be attracted towards N. Okay, so you'll have a new type of alignment of this magnetic material. So you'll give some magnetization. So you'll induce some of the magnetic properties. So this is the magnetic property of the material. So now let me just discuss about the basic idea, basic definitions related to magnetic materials. So the first is magnetic dipole moment. In a very classical way, one can think about the magnetic dipoles are the small magnets inside the magnetic material. Although it's not the real case, but for simplicity, one can consider this. So initially, when there was no idea about the atoms, no idea about the electrons, people start thinking a magnetic material as a combination of number of bar magnets. So it's a long back people used to consider magnetic material like this. Now, what is magnetic field? So you can think about a certain region where the effect of this particular magnet is available. So theoretically, we can consider there will be some number of lines of forces. So if you have certain region where the magnetic field, the magnetic effect will be observed. So this region is known as the magnetic field. So theoretically, one can think about the lines of forces or the line of forces are there. Okay, so this is the where you will get the magnetic field. So magnetic lines of forces, field lines. This is basically a imaginary line concept. So the idea is that if you have a large number of lines, more number of lines, so field strength is more. If less number of lines, so field strength is less. So this idea was initially conceived. The magnetic induction or magnetic flux density. So the magnetic flux density, one can think about, you can consider unit cross-sectional area. How many number of lines are passing? That's how many number of lines of forces are passing. Obviously, the same idea will be there. More number of lines of forces means more induction will be there, more flux density. If less in number, less number of lines of passing, so we can just consider less magnetic induction or less fluxes there. Now, what is the field strength? So magnetic field strength is considered as the applied field. You can just think about, you have a magnetic material. You can just think about a magnetic material, certain magnetic material you can consider. Okay, so now you are applying some external, you have just spread some external field over there. So some number of lines of forces are there. This will be try to pass through this. Okay, so this will be passing through this. So you have some applied field there, edge. Now due to this applied field, the dipoles inside the magnetic material will be affected by this. So this affected number of lines of forces is given by V. Okay, so this is called the induced magnetic field. Okay, so this is the relation. This is basically V and this is H. So relation between B and H is simply given as this particular relation. where mu is the permeability of the magnetic material. Okay, this is the calculation of the lines of forces one can say. Magnetic flux, the basic idea of the magnetic flux we have already discussed about this thing. Lines of forces passing through this per unit cross-sectional area is called the magnetic flux. Now the intensity of magnetization, so sometimes it is denoted by capital M or sometimes it is denoted by I. So magnetization is basically the ratio of how much the dipoles are oriented in the direction of the applied field, or one can say how much is magnetization or how much magnetic effect is left in the magnetic material divided by its initial condition, or sometimes to be denoted by per unit volume. So the magnetization is the process of converting a non-magnetic material into magnetic materials. Okay, so something is not along the direction of the applied field, but after application of the field, they are orienting in the direction of the applied field. So one can say this is the magnetization. So this is given by M, how much magnetization is there, and divided by V per unit. So the ratio, the next part is magnetic permeability, the ratio of magnetic induction B to the applied magnetic field. We have just mentioned as about B and H. So remember, H is the applied field and this is the induced field. And due to this induced field, there will be one important part, there will be magnetization. Okay, so it's the applied field, and then this is the induced thing inside the material. But among this induced field, there will be some amount of field will be applicable to retain that magnetization. So retaining magnetization is known as the magnetization. Okay. So this is B is equal to mu into H. Mu into H. So mu can be given as B by H. So this is in the case of vacuum. Okay. It's basically the measurement of lines of forces, how many number of lines of forces are passing through this. So you can just compare this thing with the relative permeability. So if you have a material and so how many number of lines of force passing through this particular material is given by the relative permeability. So it's a ratio between the relative permeability that particular medium lines of forces divided by lines of forces in the vacuum region. So this particular relation is given. Now a very important term related to the magnetic material, this is known as magnetic susceptibility. So susceptibility is the ratio between magnetization and induced magnetic field. So remember, there are three things you have mentioned. One is H, the second one is B, and the third one is M. So M is the external one, which is in the hand of the user. B is within the magnetic material. Okay, and due to the effect of this induced field, there will be something will be magnetized. Now obviously these are purely depends on the material. So for different materials, the magnetization level will be different. Okay, so the ratio between that output and the input is given by the susceptibility. So the magnetization divided by the applied field is known as the susceptibility of a magnetic material. Now an important relation, a relation between susceptibility and permeability. So you can just consider that if you are considering a relative permeability, so this can be written as the total flux density B is equal to mu 0 M plus H. Now you know mu is equal to B by H. Okay, so just replace this one and rearranging the term, one can get a relation between mu R is equal to M by H or mu R equal to 1 plus Z. So this is the relation between permeability and susceptibility of a magnetic material. Now these are the terms related to magnetic material. So now we need to think about the magnetic material with their core, with their real physical thing of this. So obviously before the idea of the atom, before the idea of the electrons, there was the people used to think about the bar magnets inside, small magnets are available inside the magnetic material. But as time passed, people start thinking about the atoms, and experimentally it was observed. So they start thinking about the effect of atoms, and it really gives the magnetic properties. So what is this Bohr magneton and what is the origin of this? So actually this was given by this famous simple idea of this particular theory. Okay, Langevin theory, where the first idea of the magnetic material comes into, or first theory for the magnetic material comes into. So let me just have a combined discussion of this Langevin theory and the Bohr magneton, and the applications of this Bohr magneton and how it can be used for the magnetic theories. So the Bohr's magneton is this Langevin theory is basically the extension of Bohr's atomic model. So in Bohr's atomic model, what you used to think about, there will be a nucleus at the center and electrons are revolving. So if you are considering a hydrogen atom, okay, at the center there will be nucleus, positive charge, and the electrons are available over there. It's revolving. On the real case, there is no revolution of electrons. These electrons are like a string and they are oscillating in different frequencies. But as far as the Bohr's model is concerned, it is revolving. So the revolving means the electron of negative charge E, it's revolving. So if you want to find the current, so one can just get that particular relation, electron charge divided by the time period. Okay, so from one point electron start, it comes somewhere here, again it comes back. This is the time period, one time period. This will give you the current in the system. So now if you know the current, in the system, now you can just rearrange this one. So this calculation is here. So this is the time period. So time period is 2 pi r by v. So r is given as the radius of this atom. Okay, and we are assuming the linear velocity of the electron is given by v. So this is the time period. One can consider 2 pi r. So you can just get current. What is the current in the system? Now, when you think about a current, so you must think about the direction of that electron. So direction of the electron in a particular, obviously, is the tangential to this. Okay, so you are just assuming the field is around this direction. Now, Langevin was considering this one, Bohr was considering this thing, that there will be a new quantity which is given, represented at mu. Okay, this is a moment. This will be considered as magnetic moment. Okay, so the magnetic moment is basically given as current into cross-sectional area. Okay. Sorry, I can just consider current. We have just consider current as capital I. So current into cross-sectional area. So now you know what is current in the system. You know what is T. Okay, so put this back, and you can just simplify this one, rearranging all that. So if you are rearranging this one, you will get an expression something like this: E R V divided by 2. Now you have V into R. So V into R can be multiplied with M. M can be considered, mass of the electron can be considered as both denominator and numerator. So if you are arranging this one, so you have a new quantity, mvr. So now you know mvr is given by the angular momentum of the system. It's a rotational system, so obviously the angular momentum plays a very, very important role. So it comes that, it's after simplification, it comes that this mu is equal to EL divided by twice of the mass of the electron. Okay, so obviously there will be negative sign because of this charge of the electron. Now just remember the angular momentum is a vector quantity and others are constant. So obviously the mu, which was known as the magnetic moment or magnetic dipole moment, it's also a vector. Now obviously the L is along this direction, so mu having a direction something like this. Now the most important thing is that if you apply some external field, okay, so I'm taking a different color, I'm showing that you are applying some magnetic field, external magnetic field around any of this direction. So it is the applied field direction H. So now there will be interaction between this H and this mu. Okay, so mu and H, they will interact, or rather you can say mu and V. Okay, so V is the induced one, H is the applied. So there will be interaction between mu and V. The both are vectors. Okay, so as both are vectors, they are having magnitude and direction, so they will interact with each other. As they are interacting, so obviously a resultant direction will be followed for this particular electron. Okay, so this is the idea about the magnetic field. So now if you are applying the field in a particular direction and they becomes parallel to each other, so you will get a high magnetic field. If they are not parallel, so you will get a less magnetic field in the system, or less magnetization in the magnet. We have considered a single atom. Okay, single hydrogen atom we have considered, but if you have a large number of atoms, so we can get a large number of magnetization in the system. Also remember, we have considered a hydrogen atom. We have a single electron, so interaction between the other electrons is quite less. Okay, but if you consider a large number of electrons, there will be effect of nucleus-nucleus interaction, nucleus-electron interaction, electron-electron interaction. Okay, and if you have a sufficiently large number of electrons, so there will be large number of interaction between the electrons. So this will help us to deviate from its mu value. Okay, but if you are considering a single hydrogen atom, so you can get a tiniest mu value from this. So this tiniest mu value is considered as Bohr's magnet. It's the orbital magnetic moment. Okay, so it's orbital magnetic moment of a single atom. If you have a single electron, single proton nucleus, so you have this. So this is the numerical value. Now you can just remember, we have mentioned this thing. This is equal to EL divided by 2. So from Bohr's magnetic postulate, it was mentioned this thing that L is also the angular momentum, is also quantized. So this is N into H cross. Okay. So the N was considered over there as a first principal quantum number. Okay, so you just replace this one. Let's replace this one and considering hydrogen atom, so N is equal to 1. So after simplification, after just putting this value, you will get N H cross divided by 2. Why H cross is equal to H divided by 2 pi. So this is the idea about the Bohr's magneton. So if you have a hydrogen, so you have Bohr's magneton, but if it's not hydrogen, then the interaction will be more, the mu value will be different from the different electrons or different atoms. Now it was observed that when you have Bohr's magneton, single electron is available. Now when you apply the external field, the most important part, so intrinsically you have this moment in the system. So theoretically all the atoms available in the universe, they are carrying some moment in the system, some particular direction of the air is there. But if you are applying magnetic field, so obviously this will affect something. Now here all the things are that they are constant thing. This really cannot be modified by applied magnetic field. But the only modification is possible with the value of v, the moment, the velocity. If v modifies, obviously you can think about either v or you can think about omega. So it's a linear velocity or angular velocity. If they modify, so L will be modified. So if L modified, so the mu value will be modified. So one can get an induced moment inside the material. So this plays a very, very important role. So if you are applying some field, there will be some modification. So this is given by a factor which is known as mu or omega L. So omega L is given by EB divided by 2m. So B is the induced magnet. Now what is this factor? So this is the additional angular momentum in the intrinsic relation. So omega, now this can be considered as omega 0 and plus minus omega L. Okay, so this is this related to the Lambda frequency. So just divided by 2 pi, you will get that frequency. So if you have this particular thing, if you have that induction in the system, and obviously when you are applying the field, external field, the circular electrons path will be modified. So the radius in this case will be modified. So initially you are considered they are circular in nature, so you have a radius of r. But after application of the field, there will be change in the velocity, so the shape of this orbit will be modified. So a correction factor is required, and this correction factor is given by 2/3 r square. Okay. So if you put these values, you will get a relation something like this. Now you can see there is a relation. So it's a relation between mu b and a b. B is the induced field. Now you know that b is equal to mu 0 h or b is equal to mu h. Okay, so that b can be represented in terms of h. Just we are representing. Now this is the effect of a single induced moment. Now if you have a n number of moment in the system, so n number of atoms you can just think about. So the total moment in the system will be simply given as n into mu. N into mu. Okay. So the total magnetization is given as total magnetization. Let me just write it. So total magnetization is given as N into mu. Now this B is written in terms of H. So now if you are writing this one in terms of H, so on the left hand side you have M and right hand side you have H. Now we have already mentioned this, since susceptibility is given as M by H. Okay, so you will have the susceptibility. This is the simplest possible magnetic material, sometimes which is known as the classical magnetic material, or sometimes called the diamagnetic. So in that sense, all the material available on the earth, they are having some movement, some angular momentum in a particular direction. If you apply the field, they will try to orient themselves. They will try to make see the effect of the external field. So in that sense, they are magnetic. But obviously, if you remove the field, the magnetization will be lost. So this is the case of a classical type of magnetic material, or it can be considered as a diamagnetic. Now, in the year 1922, there was one experiment was performed where the silver atoms were passed through. You have taken silver atom because it was something like this, that at the outermost cell you have electrons. So silver is a metal, so in the outermost cell there will be single electron. Okay, so at the center there will be nucleus, and all the electrons are balanced with each other. They are balancing the forces. So it's behaving like a single electron is moving through this, passes through this. So now it is passing through the magnetic material, so magnetic field, so inhomogeneous magnetic field. But as it was passes through this, it was observed that few number of atoms, few number of silver atoms were falling somewhere here, and few number of atoms were falling. When you switch off the magnetic field, they are falling at the same point. But as you switch it on, they are separated into two. This is one of the important things which was observed by this experiment, and this was considered as a quantum spin. And as this was divided into two parts, so one is to consider as positive half and negative half. So we can think about two energy levels are there. The type of two energy level. When field is zero, let me just draw something like this. When field is zero, this will be somewhere here. Now when we apply the field, so they are divided into two parts, two energy levels. Okay, so here V is 0, and here V not equal to 0. So they are separated. Okay, so the upper one consider as minus half, and the lower one consider as plus half. The two energy values. Okay. Now when you have the spin thing, so it is obviously the intrinsic property of spin, and when you have this one, so all the things need to be modified for the magnetic materials. So it is observed that paramagnetic materials was explained. So it was observed that some of the magnetic materials where if we apply the field, when there is no field, they are in the random form, the moments are in random form, so there is very, very less magnetization or almost zero magnetization. But as we apply the field, there will be high magnetic value was observed. So this was incorporated with the concept of spin. Okay, so this particular explanation is there. Now it's a simple idea about the two energy level, two energy state problem. Depending on the temperature, depending on the external field, this will cover the distance. So that if you are considering this energy is E1, this energy is E2. If you have number of particles N1 in the ground state, number of particles in the excited state, so you can have that equations for this. So you can write the equation, Boltzmann equation, N2 is equal to N1 e to the power minus delta E divided by kBT. Okay, so kBT Boltzmann constant. So delta energy is the difference between two energy levels. Okay, so now this comes the quantum effect over here. So apply the field, vary the temperature, so number of particles in ground state and excited state will be different. Now this is the idea about the paramagnetic material. So again, by using the statistical calculation, so this type of Boltzmann equation and the statistical calculation, one can find the susceptibility of a magnetic. So in the susceptibility of magnetic material, it is observed that it's basically proportional to inverse of temperature. So susceptibility then is inverse proportional to 1 by absolute temperature. And here all the factors are there. So this will be considered as capital C in the name of Curie, the scientist Curie. The Curie constant was known for this. Okay, and susceptibility becomes 1 by. So it's obviously it says that at lower temperature susceptibility is very high, or one can say lower temperature magnetization is large. Okay, so if temperature is low, so you have a higher chances of magnetization. And sometimes it's called the Curie's law of paramagnetic motions. So the Curie's law was also not a complete law for the magnetic material. So then comes the other magnetic relations which helps us to modify the magnetic domain relation or magnetic moment relation. Okay, so what it says, it comes with the idea about the Hund's rule. So Hund's rule is the relation between the total angular momentum. So the total angular momentum is given by J is equal to L plus S or L minus S, depending on whether the cells are half filled, less than half filled, or more than half filled. Okay, so then it can get the value of J, the total angular. So one can just think about mu B is equal to E into L divided by 2M. Now L was for the classical concept of angular momentum, but as you have got that quantum spin in the system, so people start modifying this L by considering this is J, the total angular. And as you have total angular momentum, it can be L plus S or L minus S, depending on the arrangement of electrons in different sets. Although this is not only the modification is incomplete over there, so you need to introduce one particular term which is known as the Landesi factor. So if you add this one, so you will get the complete magnetic moment for an atom when you have large number of electrons. So Hund's rule is there, and now we have taken 7 number of electrons. So how to arrange the electrons? So this arrangement is given. So this is the only way we can arrange the 7 electrons in sets. So this Landesi factor, I have just mentioned this thing, the idea about the Landesi factor. It's a correction. It's known as the quantum correction. So if you know the Landesi factor, you can calculate Landesi factor from L and S for the different atomic system, for different S values and different L values. Get that one, and you can get that moment in the system. You can get the magnetic moment. Now the calculation is simpler if you know the moment. You can easily get that idea about the total number of moment, total number of moment into the individual moment. If you multiply this two, this will give you the magnetization in the system. Okay, so if you have magnetization, so one can easily get a relation that magnetization by H. Obviously, this will either H or B, whatever you are getting. So you can get that one. So this is equal to the susceptibility. One can get the idea about the susceptibility. Now, the paramagnetic material can be explained by the concept of electron spin, by the concept of energy separation, plus and minus. Now comes the next part of the next type of material, is for the ferromagnetic. So it is observed for the paramagnetic material, when you apply the field, there will be magnetization left, but if you remove the field, magnetization becomes 0. Okay, but there was some of the magnetic material available where you are applying the field, there will be magnetization, remove the field, but some amount of magnetization left. So the magnetization left, that particular concept was explained by this particular relation. So that neat field is equal to the applied field, what you are applying, okay, the H applied field, and some part of the magnetization is left. So this is given as gamma M. So now depending on the gamma value, so how much magnetization is left from the earlier applied field. Okay, so you just put it back in the equation which was calculated for the paramagnetic material. So it's a modification in the paramagnetic calculation. So if you are rearranging this one, so one can get a relation. It's almost similar type of relation, but there is an additional term of minus theta. So theta is a quantity which will really explain the susceptibility of the material. Now a simple relation, susceptibility of paramagnetic material is C by T, whereas this is C by T minus theta. Obviously this factor, the whole factor is lesser. So this quantity is lesser. So as this quantity is lesser, so susceptibility of the ferromagnetic material will be higher. It's at some temperature, so say T value, so obviously the susceptibility of a ferromagnetic material will be larger than the paramagnetic material. So this is the advantage. But there is something else which is left for the ferromagnetic material, which is known as the domain theory, or the domains of the ferromagnetic material. The domain of what? Domains of the moment. So we have just considered the moments in a particular direction. So domains are basically the individual atoms. They are having a directional thing, a magnetic directional thing in one particular direction. Now they are in a cluster. They are formed in a cluster. So you can just take an example, something like this. Now you can see they have the atoms there in a particular direction. But you can just think about two domains, two regions. They are orienting in different directions when there is absence of magnetic field. But apply the field, they are orienting in the same direction. Now when you remove this thing, some of the things they will be in the other direction. So what is the idea about the domain? If you have some number of atoms, how many number of atoms? Approximately 100 to 150 number of atoms. Now there are two possibilities of changes. So one is known as the motion of the domain wall. The motion of the domain wall. The domain wall means this particular region is known as the domain wall. And another one is a rotation of the domains. Okay. So they are rotating. So this particular picture is given by the domain wall and the rotation of this. Now an important thing comes here is known as the hysteresis. So magnetic hysteresis occurs when the external magnetic field is applied to a ferromagnetic material. So remember, it's a ferromagnetic material. Okay, and the atomic dipoles, that's the magnetic dipole, align themselves. But when it was removed, when the field was removed, the part of the alignment will be retained. Okay, so it retains some of the magnetization. Okay, so this is known as the hysteresis. So now we'll explain this one by using this particular plot. So what is there? So in one direction you are applying field, magnetic field, and in one direction you are plotting the magnetization, how much magnetization. Instead you have the circuit, you are applying the magnetic field, and by using some system you are able to measure what is the magnetization in the system. So here this is 0. So somewhere here this is 0. So H is 0, M is 0. Okay, so there is no magnetization. And they are random. What are random? This magnetic domain, the domains or magnetic moments, they are random. So no magnetization. But as you are applying magnetic field in one particular direction. So in this case, you are applying field in this direction. So as you are doing these things, we can see more and more dipoles are orienting along the direction of the magnetic field. So it keeps on increasing. See, it's increasing. But then after that it got a saturation. So the majority of the moments are along the direction. Now if you keep on increasing the magnetic field, the magnetic moments are not going to change because they are already in the direction. Now what you can do, you can decrease the magnetic field. Now if you keep on decreasing this one, you will see they will not trace the earlier path. Rather it will track another path. And it comes somewhere here. So this is an important part. It shows that if the applied field is 0, but still there is some magnetization. So it's not fully random. So some of the moments are along the direction of the earlier applied. Now you are decreasing the field. Now what is the meaning of the decreasing field? So from this particular part you are applying the field in the opposite direction. Now the direction of the applied field is this. So earlier the direction of the applied field was this. So as you are applying this thing, it will try to orient along the direction of the field, along this particular direction. So as we are doing this thing, somewhere here, for certain negative value of magnetic field, it becomes a random. This type of thing, this becomes a random. Okay. Again, if you keep on applying the field along the opposite direction, again you will increase. You will see the increase in the magnetization. That means more and more dipoles will try to orient along this direction. Again, when it comes somewhere here, it reaches its saturation value. So the maximum of the dipoles along the direction of the applied. Again, if you decrease this one, you will see the pattern which was something like this. Okay. So this particular region shows a hysteresis for a magnetic material. So which type of magnetic material? Ferromagnetic. Now, so this is the picture, it's a similar picture. Now, this shows this particular point. So you have just mentioned this thing. So this particular point where the magnetization is retained, but the applied field is 0. Okay. So this is known as retentivity. It will retain that magnetization. Okay. And what is this particular point? What is this particular point? Here, at this is random. Although you have a negative field, this negative field, they are in a random condition. So this is known as corrosivity. And obviously this particular part for left side and right side, for this region and this region, so the saturation starts. These are the saturation starts. Okay. So this is the greatness of a ferromagnetic material. Now I have just mentioned what is the idea about retentivity and what is the idea about the corrosivity. Now depending on that area, so one can just divide the ferromagnetic material in soft magnetic material and hard magnetic. Depending on the application, you can choose whether you can take a soft magnetic material or a hard magnetic material. So it's in simple way one can sense the magnetization and demagnetization is quite easy in case of soft magnetic material, but hard is difficult. Okay, there will be some heating effect in the hysteresis. So there will be some losses. And the soft magnets are temporary magnets, where the hard magnets are the permanent magnets. So which are available on the earth, they are permanent magnets. Sometimes electromagnets. Okay. And the most important part, hysteresis loop is small. Remember, hysteresis loop is small. Here hysteresis loop is large. And retentivity, corrosivity value, obviously this should be small, but the area is small, so the these values are also small. But here these are high. This particular picture is for the soft and hard. So now we can compare three types of magnetic material: dia, para, and the ferromagnet. So here, what is observed? What is the most important part? The most important part is the what is the domain, what is the main thing about that magnetic material. So here, for the diamagnetic material, it's the orbital motion. Remember it, it's orbital motion. For the paramagnetic material, it's unpaired electron. And this is the exchange interaction between the unpaired electron. Remember this particular picture. This particular picture. So the magnetic field, they are not separated, and as you have applied the field, they are separated. So there will be some exchange interaction for ferromagnet. Now about the data, their susceptibility value is negative. Okay, it's small and negative. Okay, whereas the susceptibility value of the paramagnetic material is positive, but it's not that large. It's obviously larger than the diamagnetic material, but it's not that large. But ferromagnetic material, this is very large. It's quite large. Okay. And this is almost temperature independent, whereas the susceptibility of a paramagnetic material is inverse to the temperature relation. This is also inverse to temperature relation, but obviously we have a T minus theta relation, so susceptibility is more in case of ferro. So the examples are the copper, water, bismuth, and the superconductors are a very good diamagnetic material. Aluminium, lithium, sodium, they are paramagnetic. Iron, cobalt, and nickel, they are ferromagnetic. So magnetization, demagnetization in the external field. So magnetization parallel to the external field, obviously the paramagnetic material is present. Magnetization spontaneously in the absence of external magnetic field. Now depending on the application, the retention of the magnetic field, the diamagnetic material, obviously it's not retaining any sort of magnetic field. Paramagnetic, it's also not retaining. But in case of ferromagnetic, it retained magnetization. So retentivity value is there. Okay, we have already mentioned about that exchange interaction. So applications are there: diamagnetic leviation there for the ferromagnetic material, for the diamagnetic material, for the paramagnetic material. So medical imaging and compass we can use. And for ferromagnetic, it's one of the important one, electric motors, okay, the hard disk and transformer. So magnetic disk will be used over here. This is the application. So now you can see, although you have better theory, better control over the ferromagnetic material, but the dia and para also having some application, which is very, very important. Now there is the idea about the antiferromagnetic material and the ferrimagnetic material. So now you can see from this particular picture. Okay, so for earlier cases, you have considered only one direction of the movements. Okay, now you can see they are in opposite directions. So you can think about two atoms placed side by side. Okay, so one atom having a moment along this direction, another atom, just consider another atom over there. Okay, another atom you can just think about. So its moment is in the opposite direction. Okay, so obviously this will cancel each out. This will going to control this one. So zero magnetic moment resulting in a zero magnetic moment. So very less magnetic moment. So you have more control over this type of magnetic material. Now obviously depending on the magnetic material you can use this. And obviously it's a temperature dependent. The same type of relation is over there. Okay. Now we can see this is also some additional term E plus theta. Okay. So as you have this thing, so it susceptibility value changes. It decreases with increasing temperature. And you can just think about the ferrimagnetic material. Now you can just see the comparison. So the moments are not of equal values. Okay. So you have two moments, one in this direction, two atoms are there, and another is in the opposite direction. But obviously they are not cancelling each other. In earlier case in the ferrimagnetic material, the domain values are equal, so they are cancelling each other. But in this case, they are not able to cancel each other. This is the picture which helps us to explain diamagnetic material, paramagnetic material, antiferromagnetic material, ferrimagnetic material, and ferromagnetic. Just look at this picture. When H is 0, they don't have any moment. Apply the field, they are trying to orient in opposite direction. Something is there, some magnetization is there, but this is negative. Paramagnetic, you can see it's a random in nature. Apply the field, they are trying to orient in a particular direction. Okay. Now come to the ferromagnetic material. Ferromagnetic material, when they have certain orientation, apply the field, they will try to orient in a particular direction, the direction of the magnetic field. Now we can see for the antiferro, they are in opposite direction. And for the ferrimagnetic direction, they are in opposite direction, but the magnetic values are not equal. Okay. So this is the explanation of the spin alignment of the moment alignment. The examples are given there. Already we have discussed about the examples of dia, para, and for ferromagnetic material. For ferrimagnetic material, Fe3O4, yttrium, iron, they are the examples. And for the antiferro, this is the example of chromium, NiO, and Fe. Again, we have this particular picture, a simple summary of this one. So diamagnetic material, this is the direction of the applied field, this is the direction of the moment. Now paramagnetic, this is the direction of the applied field. Now they are directing along the direction of the applied field. Ferrimagnetic, they are directing along the direction, obviously. Okay. So if you, in case of paramagnetic, if you switch it off, so they will be random. But if you switch it off here, they are not random. They are maintaining their direction. Okay. So the ferrimagnetic and antiferromagnetic, obviously they are in opposite direction. Antiferromagnetic, they have equal magnitude values in opposite direction. But here they are opposite direction, but the magnitude values are not equal. Now this is a simple picture of susceptibility as a function of temperature. Diamagnetic material, it's almost temperature independent. Susceptibility value is very less and it is negative in nature. So you can see the diamagnetic values is somewhere here. It's not changing with time. It's a long temperature range you can consider. It's almost invariant. Now we can see the green color, it's a paramagnetic material. Obviously it's a inverse to temperature. So it's 1 by T. As temperature increases, the susceptibility value decreases over here. Okay. Now we can have ferromagnetic material. Okay. We can have ferrimagnetic material and antiferromagnetic. So in all cases, there will be something value plus minus some factor over here. So obviously when they are equal, susceptibility value will be different. So they will change. They will observe a phase change over. Okay. So now you can see all are moving from this ferro, this antiferro materials. They are converting at certain temperature. They becomes a paramagnetic. So at low temperature, they are showing their properties. But then after that, after changing the temperature, they are showing the paramagnetic. Okay, now this is the idea about the Curie temperature. Curie is defined as the temperature at which a certain material loses their permanent magnet and it will to be replaced by the induced magnets. Nil temperature, Tn, the temperature or the magnetic order temperature is the temperature above which an antiferromagnetic material becomes a paramagnetic. Okay, and for the ferrimagnetic material, a paramagnetic phase to the ferromagnetic. So it's a phase transition. Now the last part you need to talk about the various application of the magnetic material. So we are really surrounded by the magnetic. So one of the important things, the magnetic disk, the hard disk which are there, it contains the magnetic materials. Okay, so you can see those magnets up there. In CD-ROM, you can see if you have earlier the CD-ROM, DVD-ROM, they will be there. Even in the hard disk also there will be some magnets. Okay, the speakers, what you are using, so they contain some permanent magnet which helps us to give a good quality of sound. Okay, so the transformer and this particular picture, we are all familiar with this thing. This is the production of light, the production of current. Alternative, you have permanent magnet, armature is moving, it's rotating, so it's cutting some flux, magnetic flux, you will get current over. Now some of the simple examples, obviously the cranes, this will carry some heavy loads. They can be used as a separator if you have a mixture of some grains with some metallic things. So if it passes through the magnetic material, so they will be separated. So they are easily separated. Now one of the medical use in the MRI scanning, okay, magnetic resonance imaging. So this is the picture. One patient can place over there. A high magnetic field will be there, so you can get a very good picture. Now this can the debit cards. ATM cards, sometimes the keys are also given by this magnetic strips. You can see black magnetic strips over there, which really helps us to have a high secure money transaction or high secure transaction in other format. Obviously the compass, earlier days people used to use compass. Nowadays we don't need this one. We have a satellite communicating system, so we can easily use this thing. But obviously the compass is useful. Now the last one important part is the ferro fluids. So the idea of the ferro fluid is that some sort of base fluid will be taken inside a container. Okay, so you can just think about some sort of base fluid is there. Okay, and there will be some of the nanoparticles, some of the ferromagnetic particles are there. This dimension of the particles are in the nano range. Okay, so 10 to the power minus 9 meter range. Okay, so now they plays a very, very important one. So they can be used for the magnetic lubricant and they can be used for the hard disk systems. Okay, so magnetic lubricants can be placed over there, or ferrofluids can be placed over there. So the advantage of them is that as it contains some of the base fluid, it will carry the heat. It will minimize the heat in the system. In the hard disk material, so the heat will be generated, but this will be minimized. So this is the picture. Okay, so by which one can produce the base fluid. You can take that material, so apply the field. It can use in number of applications. Okay, so these are the things shown. Okay, thank you. So we have discussed about the magnetic material. Okay, we have discussed about some of the magnetic definitions. Okay, and then we have discussed about some of the magnetic materials, the basic theories of the magnetic material. Okay, and then we have discussed about the types of magnetic material, a simple comparison between different types of magnetic material, and then at the end we have some idea about the susceptibility as a function of temperature, domain explanation, and that spin, okay, the magnetic spin relation, and then at the end we have the application of magnetic.